the picture. So your coils are going to be in the base here, and you want to center your sample on there. This light will flash. So let's actually measure a sample. This is from my research. When you do this, you don't want to have metal on the sample because that can actually interfere with the eddy current sensors. So you usually need a silicon sample without contacts yet. I didn't calibrate it, but just for explanation purposes, we'll do that without that. Let's just call this test. You don't have to do anything with this for homework. I just wanted to show you. So you input your name, the thickness of your sample, and that's important for counting or measuring the resistivity, which you also input as a reference starting point. And then you'll just hit measure, and you'll see this light will flash. If it's not broken. Yeah. And so it'll give you it'll show you the slope of that illumination and also the slope of the photoconductance within the sample. And you can use that to find out the inverse lifetime versus the carrier density. And that carrier density can tell you the lifetime of your sample. You can change that carrier density to see how it would work. I think some of the best passive samples in the world are at like 8 milliseconds. You can see this one's only at 400 microseconds, so not quite there with this one, but really any passivation around 1,000 is great. Beyond that, it's kind of diminishing returns on what you get. So that's that. If you have any questions about that, I can answer later. This is our solar lamp, and this is our Keithley that's used to measure our cell. So we're going to use the same computer for that. Sorry, so what's that? So we have an IV measurement program from, actually Lynn helped us get this one. Someone disconnected. I had this all set up and then someone used it, I guess. So the Keithley's connected to the computer using a GPIB. It's a graphical interface switch, kind of expensive. So I need to restart this. Doesn't get any bigger. So with this program, you can tell it which voltages to sweep across. It'll control the Keithley entirely. So you can set your voltage range, the number of points you want. The compliance voltage is to make sure not too much current goes through your cell. Let's say you go too far in voltage and your compliance is like 5 amps, you could destroy your solar cell. So you want to be careful to, if you don't really know how something's going to perform, smart with small voltages, low compliances until you know that what you need. So the Keithley will connect to a solar cell. We've got one under the lamp here, but I haven't turned the lamp on yet. So it's kind of a mess here, sorry, but there's a cord coming out of that solar cell, and there's actually 4 terminals on that, and we'll get to why in a second. Okay, so red input, that's going to be your positive terminal in the solar cell, right? The black as our low. So I'm going to choose the outermost ones. I think those are on the same. So we have our cell. If you want to go ahead and click measure, or here, skew. You can get a dark ID curve. So there's still light in the room, but it's not connected. Let's get messed up. So yeah, immediately I knew it's not connected because that doesn't look like the dark IP stuff we talked about earlier, right? So there's our dark IV slope, right? We have no current, no negative current, but we still have that familiar shape. Save it. we can, so this is nice, this program, if you click this solar cell button, it'll calculate all of those parameters for you that we discussed earlier, so that saves me a lot of time. But I think it's important to learn like how you find those and where they come from. So we save that. On keyboard. Okay, so that's under dark. So here we have a solar lamp. This is the rating on this lamp. Different lamps will have different ratings. I forget exactly what the rating is, but it's a pretty good lamp, and it also has collimating optics in it. So that means the beam comes out with it's nice and straight all the way down. It doesn't disperse like a flashlight would or something like that. And that helps you so that the height where this is isn't so important. So turn the lamp on. There's a shutter to protect your sample while the lamp's warming up, but we're not going to bother warming it up. So here's our reference cell. You can see it's actually just this tiny little circular piece of silicon in the center. But yeah, so we have that. We can do our measurement again, and we'll see. So you just drop down. We have current, right? And if we hit our solar cell button again, it'll calculate all that stuff for us. So 3% efficiency, 66 fill factor, VOC at 443, so that's pretty low millivolts, and the JSC is around 10. So buying actually one of these isn't very expensive, but paying for someone to measure it properly using the setup with the cooling and all that costs like another $200 more for someone to do this. But we have this sheet that'll show us what they measured it when it left the factory is. And so, our VOC is pretty close. It's at 488 here, 443 here. Our ISC is supposed to be 5.4. Our ISC on here is, that's in amps, but 4.8. So it's much lower, or not much lower, but it's quite a bit lower. So our JSC is low when we're measuring this. What does that mean for our solar cell?
High shunt resistance.
Could be high shunt, yeah. Or another thing is our lamp could be not at a high enough power. Like it's not outputting 1 sun. It could be putting out 0.7 sun or something, and that's what's causing our loss in current. So we can also up our current here. If I can remember how to do that. So we can turn our current up to, let's say, these are in watts, so it's kind of arbitrary. It's just the wattage across the bulb. So we'll save this one first. Okay, so we'll measure again. So currently our JSC is 10.2. Right? We just increased the light. And now our JSC is 12.29. So we've increased the current by increasing the amount of light intensity on the solar cell. So that's what we wanted. That's good. That's probably too much. Yeah, we increased the JSC too much, but we can hone that in nice and perfect. So this cell has 4 outputs. I've only hooked it up to 2 of them. Does anyone know why you'd want 4, or what it'd be used for? The Keithley also has 4 ports. Has anyone done every resistance measurements or anything like that? So if you measure with just 2 probes, it's actually kind of a crude measurement. If you use 4, they can compare the resistances between each line and remove that, so you have a much lower, you'll have a much lower VOC, and that helps you get more efficiency. So if you measure with just 2 probes, you might have more resistance than you want, and that's not due to your solar cell, but due to the leads connecting to it. So this can help you out with that as well. The only issue is I don't have the right probes, so it's kind of a pain to get these all connected. Yeah, this thing's not made for, I need alligator clips and not whatever these are. So we can try all 4 probes. Yeah, I don't know if I'm gonna get them all in there. Might have to take my word for it. Okay, so that's all hooked up. So if we see our so it's calling it RSC and ROC. Does anyone know what that means? Yeah, right. So it's resistance at short circuit and resistance at open circuit. I don't know why it doesn't call them shown in series. I guess it's just shorter to do that. So we'll save that light too. Okay. So we'll do one more measurement. So I've hooked up all 4 probes. There's a sense mode where you need to change this to a 4-probe sense. That's just so it knows you have another tube connected, and it's going to do the calculation for you. So if I have to save, what was our ROC? Huh. ROC actually went up, so something's not right. Usually it would go down, so something's messed up. Probably one of these isn't connected properly, but since it's kind of tricky to fiddle with that. All right, so we have the IV data, we have illuminated data. It's not quite accurate to this, but that doesn't matter. You can still calculate everything because it's still got an efficiency to it. So yeah, this program can do a lot of different things. You can do different solar cells. You can do diodes as well. Instead, you measure kind of the intensity from that as you sweep the voltage or do other sweeps like that. So we usually use probes like this with metal contacts on a sample to measure like a real sample. Maybe I can demo that real quick. I don't know. Do you guys want it? Are you guys bored? No. So this is just a piece of solar cell here from another school. I think this is from Arizona State. What we can do is use these 2 probes here to measure that. So I'm going to mess this up. So I'm just going to kind of pick a random spot on the bus bars to do this. So this is going to hopefully probably not give us good IV characteristics. I don't think it's a very good piece of solar cell that we could have, but it was for another application. So with this one, since they're both on the front, oh shit. You normally want to measure to the back of the cell. That works. So that's linear, right? Can anyone guess why that is? What did I do wrong? But it's actually pretty ohmic too. If we just hit resistances. It's not too bad, 158 ohms. Any ideas? So I just measured across the bus bar on the front. It's one strip of silver, it's just like a wire. So it's not going to work that way. But, you know, if we measured from, like, let's say the silicon to the bus bar, what do you think would happen? Linear or diode? Not a good time. Also the same thing. So I can't make contact now. So I think the reason that is because if You notice the surface of this is actually blue. It's got a silicon nitride layer on it, so that's an insulator. So basically one probe's on an insulator, one probe's on the metal contact, so we're not going to get a current unless we crank the voltage pretty high, which might damage it. Yeah. Any questions anyone has? You guys want to play with the measurement at all? Or?
So how do you measure that so that it would be IV curve?
This one? I actually don't think it has a back contact. We were using lasers to fire in the back part of this. So I think the back is just blank. Yeah, so there's just nothing on the back there, so this one's not going to have... This one they've done screen printing to deposit silver lines on there, and then we'd use the laser to fire in those lines to make contact through the nitride to the silicon. But this one hasn't been fired through, so it's not going to work very well. I don't have any cells on hand that we can test besides the reference cell. But yeah. Yeah, that's about it. That's all I got, really. This is an EQE, so you're doing the homework now. Some of you turned it in already. So you can measure EQE or IQE with this. It's a similar thing. It's just a lamp, but there's a grading that'll select the wavelength of the light, and you can just measure your efficiency as a function of which wavelength of light you're hitting it on the sample. So you can measure IQE, EQE, so we can do that as well. We have the Syntin and the lamp, and yeah, that's pretty much it. We have one other lamp back here. It's actually not working, but this lamp's a little different in that the light's coming from the bottom. Does anyone know how you'd want to do that instead of having it come from the top like that? I guess it might help with that. We do a lot of, there's a solar cell called the all back contact, or IBC, interdigitated back contact. And so if you have all your contacts on the back, you want to position these probes on the back of it, and so put the cell actually face down, and so you can get the probes there easier without, because if you had it face up, it's hard to get the probes underneath to get that measurement. So yeah, we have a variety of probes. So these are just 2-point probes, but we also have these 4-point probes. They're tiny little claws like that, and that can do the same thing as the 4 connections we had here as well. So yeah. So just to recap, if we have the light off, we get the dark IV. If we have the light on, we'll get our IV. If we increase our intensity, we get a more increased J0 and increased efficiency, but the VOC will be the same. If we use 4 probes, we should get a lower VOC, or sorry, resistance at VOC. And yeah, I think that's about it. Any other questions? Okay. Does anyone want to mess with anything? Play with this solar cell? No? Okay. I think that's it.